Hello and welcome to the next part of our quick run through the features of the dasim simulator. This time having a look at the transient simulations. That's doing a simulation for circuits which change their value as a function of time. The currents and the voltages are not constant, they change as time goes on. Once again, let's go back to the simulation screen. And let's build a circuit which has as its behavior a function of time. Let's try this one. How about a voltage source that goes through a resistor onto a capacitor? Now, in the simulation world, in the transient simulation world rather, the voltage sources have a value of 0 until time t equals 0, until 0 of time. And then it would suddenly become a 1 volt voltage source. So, in a transient simulation, what we have here is a voltage source which is actually doing something more like this. As a function of time, voltage, it's 0 for all times until time equals 0, and then it shoots up to 1 volt, and then it remains at 1 volt from then on. That is how this DC 1 volt voltage source is interpreted when you are doing transient simulations. What would happen in this circuit, therefore, is that at negative times, there is no voltage in the circuit, there would be no charge on the capacitor, the voltage would be 0 everywhere. But as soon as the voltage at this point goes up to 1 volt, then current will start to charge the capacitor, current flowing through the resistor, and the capacitor will start to charge up. And we can simulate that using a transient simulation. Select transient response mode. Immediately we get a warning. The transient simulator can only output traces based on the readings of ammeters and voltmeters. So if we want to see what the voltage is across the capacitor, we need to put a voltmeter across the capacitor. So let's do that. Connect the other side of the voltmeter to ground. Effectively, that's the same thing as connecting it to this point there. Okay, back to the transient simulator. Our warning has gone. We can now press start, and it will start to do the transient simulation. Okay, there we go. I'll just expand that again so we can have a bit of a better look at this. I can control the scale on the y-axis by the control here. I can move the traces up and down just like you can on an oscilloscope. And I can expand the time base like so. You'll notice that the transient simulator will run for a certain amount of time and then stop. And the certain amount of time that it runs for is a function of both when it thinks that everything interesting has finished and all of the voltages and currents in the circuit are stable, or it thinks it spent too long trying to calculate what the circuit is doing. In this particular case, the transient simulation has stopped at about this time here. You can see on the tooltip that's about 180 microseconds. If you want the simulation to keep on going longer than that, you just press the continue button and it will continue for another set period of time. But in this particular case, there's no point in doing that because everything has pretty much stabilized. The interesting point here is the shape of this curve as it goes up, as the voltage changes across the capacitor. You'll notice it's not a straight line, it's a curve. And the equation of that curve is a very useful thing to be able to derive and to work with and know. Other points to mention about the transient simulator: you could replace this voltage source here, this DC voltage source, with an AC voltage source. And an AC voltage source in the transient simulator is assumed to be a source which is 0 for times up until time t equals 0, just like the voltage source, but after time t equals 0, it starts oscillating up and down at 1 volt. So if we run this through our simulation now, reset the simulation, start it again, we get this. And I'll just expand that, and you can see that something interesting is beginning to happen. It shoots up to around 1 volt, just as it did before, but now it doesn't stay at 1 volt, it starts to come back down again. And if I continue with the simulation, I'll have to move this up and change the scale a bit in order to see what's going on. You see, the output, the voltage across the capacitor, is now a sine wave. It's going up and down, reflecting the fact that the voltage on this voltage source is going up and down as well. I can plot as many plots on the transient simulation output as I like. I could, for example, take another voltmeter here, attach it across the voltage source, and then I could see both the voltage source and the output on the transient simulator. I'll have to reset so that it picks up both of the meters and then start again, and there we go. You see that right at the beginning the AC circuit has shot up to 1, and then it starts going oscillating up and down, whereas the output takes a little while to be charged up to the voltage coming out of the voltage source here, but after it has managed to catch up, they track each other pretty accurately up and down. This, of course, is a function of frequency. If this was going at a different frequency, then the behavior of this circuit would be quite different. And you can control the frequency once again by going into here, and maybe I should shoot up to, oh, I don't know, let's say 100 kilohertz instead, and try and run the simulation again, but this time our oscillation here isn't going at, it was about 900 hertz before, now it's going to go at 100 kilohertz. Start that. And we get something a bit more interesting happening. You'll see that now the output across the capacitor is not in phase with the voltage that we're generating here. It lags a bit. The output here reaches its peak after the input voltage that comes from the voltage source reaches its peak, and so on. We'll do all the theory and try and understand why this is happening later. This video is just supposed to be about the simulator and how you can see these things. You can grab this little diamond here and drag it back, and you'll see that wherever I put it, the displays of the meters on the screen reflect the voltages and the currents at that particular point in the simulation. So right back at the beginning, there's no voltage coming in, there's no voltage across the capacitor. As you start to move to this point just after the beginning, the output here is, oops, a little bit off that, nearly 1 volt, and the voltage across the capacitor, a little bit under 200 millivolts. It's beginning to go up. And they oscillate up and down like so. There are cursors that you can put on, so you could measure, for example, the period of the oscillation. put one at the top, drag the other one, just click and drag to the top of the next peak of the purple waveform. 10 microseconds is 1 period, so the frequency is 1 over 10 microseconds, which is 100 kilohertz, if we didn't already know that. There are voltage cursors as well, so you can measure voltages, and you could see that, for example, the peak-to-peak amplitude, that's the difference between the maximum possible output and the minimum possible output here is around about 1.69 volts. If we had an ammeter here, we could do a similar thing, only with currents. The tooltip is this display that comes up saying that at this point here, for example, we are at 30 microseconds and the cursor is pointed at the point of 970 millivolts. I can turn that off if that is distracting. Interactive mode slows down the simulation so that it goes quite slowly. Now this means that I can change the circuit during the simulation and then wire it back up again, and the simulation will keep going. You'll notice that when I disconnected the capacitor, the voltage on the capacitor just remained constant, because there was no way that any charge could flow onto the capacitor or flow off it again. And it allows you to actually change and move components and change the values of components in a simulation while the transient circuit is still running. It can be quite interesting to try that sort of thing and see what the effects are. Right, I think that's everything that you need to know to get started with the Transient Simulator. Next time, we'll have a look at frequency and step responses.